more. So let me communicate what I've learned. So I'm basically following the article by Cato, the first one where he introduces log geometry called log structures of Fontaine-Illuzy. Now I also looked up various things in here, but this is Augus's notes, but I decided life was too short to read everything in there. So I want to start by talking about some morphisms of schemes with no log structures at all in sight. Now these are going to be morphisms that are not smooth. So let's start with some examples. So let's take the map from A1 to A1, and this is going to be a coordinate here, S and T, given by T equals S squared. So the usual double map from A1 to A1, of course ramified at 0. And let's, if you want to understand whether something's smooth or not, you should look at what it does on differentials. So let's have a look at the sheaves of differentials on these things. So omega 1 of A1 over the field K, so the field K. It's a free module. It's a sheaf, but this is A1, so it's just a module. So it's a free K of T module, say. Generated by dt. And so what happens if you look at the map on differentials induced by this morphism? Well, what do we have? We have omega 1 over k to omega 1 a1 over k, and dt here, pulled back under this morphism, gets sent to 2s ds. Okay, so this map of modules is not surjective. It has a co-kernel because we've got an S here. So the co-kernel is something that's supported at the 0 point in this A1.
Are we from characteristic 2?
Yes, indeed. Thank you. Yeah. So this map is actually etale outside that point, and so if this were an isomorphism, then this map would be etale, but it's not because at this point there's some co-kernel. Right. So let's look at some different sheaves. So sheaves of logarithmic differentials were something that was defined before log schemes came into existence. And what are they? So let's instead consider log differentials. Okay, so we've got a thing called omega 1 A1 over k, brackets log p. P is going to be the point, right. Well, let's call it, yeah, t equals 0 for now. This is by definition, it's a sheaf, so it's a module in other words, and it contains this, and it's contained in the thing over the function field. And it's just slightly bigger than this one. So this is it's the free KT module generated by dt over t. That's the definition of it. Okay, so let's have a look at what this morphism does on these two sheaves of logarithmic differentials. This point is going to be called P in both cases. Never mind. So dt over t, well, dt gets sent to s ds. So this gets sent to 2 times ds over s. And this is an isomorphism, because we're not in characteristic 2. So so whatever these sheaves of logarithmic differentials are doing, we found some sheaf of some kind of differentials on which this map induces an isomorphism, which it didn't do on the regular differentials. Okay, so that's example 1. Example 2 is going to be a blow-up. Take A2 to A2 with coordinates x, y here, and u and v here. U is x and v is xy. Okay, so then let's look at the regular differential first. So omega 2 A1 over k, no, other way around. Omega 1 A2 over k is Fourier rank 2 generated by dx and dy. So what do we have? We have omega 1 du goes to dx, and dv, well, we'll use the Leibniz rule, goes to y dx plus x dy. Okay, so I mean this thing is, again, it's definitely not surjective. There's something weird going on here. So as soon as x equals 0, then this thing has a cokernel. So it has a cokernel supported on the locus where x equals 0. Okay, and let's let's look at what happens with log differentials. So we're going to let d to be the divisor xy equals 0. And then by definition, omega 1 a2 over k log d is generated by dx over x and dy over y, by definition. And let's just notice, so in the case of A1, if I just, in the brackets, put p instead of log p, then that would have just been differentials which have a simple pole at p, and I would have got the same thing, I think. Whereas here I really wouldn't. I don't allow, for example, dy over x. That's not in here. So this is strictly smaller than just allowing poles of order 1 along x and y. Okay, so here's this module, and what happens? Well, du over u goes to dx over x, and dv over v goes to, so it's a simple consequence of the Leibniz rule, but a fun one, that the map sending f to df over f is actually a homomorphism that takes multiplication into addition. So this ends up going to dx over x plus dy over y. Okay, so this thing is again an isomorphism. Okay, so this seems like a fun trick. I want to do one more example, which is going to be relevant later, which is very closely related to this one, which is map A2 to A1. Defined by t equals xy. So I can get it by doing this and then just projecting onto v. And this is a family of things, because above t equals 0 I have a singular fibre, that above all the other things I have a hyperbola smooth fibre. Okay, so this is a family of smooth curves degenerating into something with a double point. And what happens here? Well, we have the map from, let's do the regular differentials first. And we get A1 to omega 1, A2, and then dt to, again, y dx plus x dy. So this thing always has a co-kernel, but the co-kernel is of rank 1 outside x equals 0. No, it's rank 1 apart from at the point 0, 0. And at the point 0, 0, then it suddenly becomes rank 2. So. And indeed, this map is smooth of relative dimension 1 outside this point, and then it's not smooth at that point. So this is kind of what you would expect. What happens with the logarithmic differentials? So I'm going to use the same log differentials with respect to d here and with respect to p that I used before. And then dt over t maps to dx over x plus dy over y. And so this is just a straightforward inclusion of a direct summand. So so co-kernel is free of rank 1. Okay, so 3 different situations, all things that we might be interested in. And in all cases, when you look at these sheaves of logarithmic differentials instead of the sheaves of regular differentials, you find nicer behavior. And so, as I understand it, one of the motivations for defining log schemes was, can we define these? Is there something on which these sheaves of log differentials are just sheaves of differentials? So we want to change the structure of the underlying scheme so that these things that we're looking at here are just the sheaves of differentials on these things. Because then you can do things like Durand cohomology, hypercohomology stuff. So I understand that one of the original motivations was to be able to understand degenerations in Durand cohomology or in crystalline cohomology, where you want to be able to talk about differentials degenerating on special fibers. So that was motivation. Okay. So hopefully that now motivates the definition of differentials on log schemes. Okay, so I haven't talked about the relative sheaf of differentials here. I mean, in each case, the relative sheaf of differentials is just a co-kernel of this map on differentials that I've written. So let's take f from x to y, a morphism of log schemes. So each of these is a scheme that comes equipped with a sheaf of monoids and a map into the unit sheaf. No, map into the structure sheaf. So we need to give these things names. So let's have alpha is going to be the map from M to OX, the log structure on X, and the log structure on Y is going to be beta, which goes from N to OY. So the idea is we want to define n over 1 x over y, the sheaf of relative logarithmic relative differentials on these log schemes by taking omega 1. So I'm going to do the obvious thing of writing a line underneath to mean the underlying scheme. So we want to take this, but then we want to add a little bit more. So taking this thing and adding a thing called d log of x. So d log of x is commonization for dx over x. Now this thing, of course, doesn't make sense. Well, maybe say what x is. For x in the image of this map here. So this thing doesn't make sense. Maybe in the differentials over the function field it makes sense if the thing's integral. But we're just going to formally join a thing called d log of x. And the idea is that that's basically what we were doing here. Because if we take the log structure associated to the divisor in each of these cases, we're just really formally adjoining something of the form dt over t, dx over x, dy over y, where these are the things that cut out the divisor. Okay, so that's the idea. Let me give a formal definition because I should say something actually exactly correct. So formally, there are different ways to do this. I'm just going to follow what Kato does. Let's define omega 1 x over y to be the quotient of, so I'm going to take omega 1 of the underlying schemes, and I'm going to take the direct sum of that with OX tensor over Z with the groupification of my monoid M. So things in here just look like sums of a regular function times an element in the groupification of this monoid. Right, so an element here, if it's A tensor B, you should think of it as being A d log B. That's the idea. And now we need to add some relations because the d log things interact with the differentials that we already had in some way, so we need to encode that. So what are the relations? There's two types. So if I have an element of the monoid, I can map it in and I get a function, that's alpha of A, and so d of that function should be the same as d of this function should be the same as the function times d log of it itself. That's saying that d log of it is the f over f. Okay? Now this should happen for A and M. And I've made no mention of y or n so far, so this is meant to be a sheaf of relative differentials, not some kind of absolute thing. So I also want to quotient out by things that come from below. anything that comes from below, so if alpha's in the image of the map from F inverse n to m, then I want to set d log of it equal to 0 in this thing. Okay, so an idea is, say, think this element is d log of, well, alpha of n. So formally I'm drawing d log of each of the functions in the image of this map of monoids. Okay, so that's the definition.
Can I ask about this m, the fact that you took the groupification of m? So in your examples, this is like d of log of 1 over x or something? That feels like...
What is?
Because, I mean, because x lives in, x is the image of something in m.
Yeah.
And so 1 over x is in the image of, 1 over x feels like it should be in the image of m group, even though there isn't a map from m group.
The d log of 1 over x is minus d log of x.
Yeah.
Oh yeah, okay.
That's true.
And that hopefully follows from the thing that we... Cool, thank you.
Yeah, I think that follows from the report. Okay, so a few comments. So I said this was exactly what we did before, but actually that's not true. Here we just adjoined d log x and d log y, and here they're not the only two things in the image of this map of monoids. There's a whole bunch of other stuff, because this is a log structure, so the whole of the unit sheaf is in the image of this map of monoids. Now, this means that you don't need to bother adding those things. So, in other words, if I take a pre-log structure, I get the same sheaf of log differentials as if I take the associated log structure. I get the same thing. So we can use pre-log structures for m and n. And get the same result as for associated log structures. So you don't care what happens to the units. You can forget about the units because they're already taken care of. If f is a unit, then df of f is already there in the sheaf of differentials. And let me just state that if it was one of these things, so if the log structure comes from a divisor D, then we get the sheaf of logarithmic differentials as before. So I didn't find this explicitly stated anywhere, but it seems to be a pretty easy consequence of this. Okay, and Kato gives another description, which I'll write because it might be useful. So let's say, so this is in the case where we're just looking at the spectrum of a, I was going to say the group ring of a monoid. I guess it's called the monoid ring of a monoid. Yeah. So if P and Q are monoids, and then I'm going to let X be spec of R of Q, and Y spec R of Q for some ring R, and F from X to Y is going to be induced by a map by a homomorphism from Q to P. And then there's another description for this thing. Then omega 1 x over y is OX sense of weirdness, I just take the quotient of the groupifications of these two monoids. So P groupification or the image of Q groupification. And we're going to see that this is a very important case. Okay. So let's move on to smooth and etale morphisms of log schemes. Yeah, I've been talking about differentials a lot. As you do with schemes, I'm actually now going to define smooth and etale not using differentials at all, and then relate them later back to using differentials. So we're going to define them using this infinitesimal lifting property. And the definition is going to be exactly the same as for schemes, except I'm going to write the word log in some places. Okay. So let's have a diagram. Let's have a map from x to y, or f. And let's have a map from something called t to y. And let's have something called t prime. And this is going to be a closed immersion. Defined by an ideal of squared 0. Okay, and I suppose I've got a map from the smaller thing into x, and then the question is whether it extends to a map from the larger thing also into x. Now I'm going to write another condition here. I'm going to write that the monoid, the log structure on T prime, is the pullback of the log structure on T. There seem to be many variants of this definition. It's not clear to me whether this is actually necessary, but I'm going to make the definition with this thing here, just to be safe. So what's the definition? It seems to make sense. I mean, surely you can't just take any log structure on these
diagram to be Cartesian for log schemes.
Not going to be Cartesian.
No. Anyway, I'm going to leave that condition there.
Do you want T and T prime to be affine or something like that?
Actually not, because I'm going to only insist there's an etale locally lifting.
Oh, okay.
Right. As I say, there are many different ways we can phrase it.
Sure.
Yeah. Yeah, I'm doing what Carter does, but you're completely right. I could restrict to affine things if I wanted to. So, definition. F is smooth. So, as usual, if you just use this, then you get a property called formally smooth, but we want smooth. So we're going to say F has to be locally a finite presentation. And this lifting property. And there exists a lift T to x, etale locally on T, for all such diagrams.
So does this mean like etale locally on the scheme underlying the manuscript?
We haven't defined etale yet, so I guess yes. Yeah. Yeah, I think so. Yeah. Okay, so this is the same as the definition of a smooth morphism of schemes, apart from, yeah, maybe we want to do it with affine things. So what you do to make etale instead, you just say etale here, and then you say unique. Okay. Okay, so that's the definition. It doesn't look like it has very much to do with differentials, but formally all of the theorems you now prove about smooth and etale things look exactly the same, and the proofs look exactly the same as when you do the corresponding things for normal. I don't mean normal schemes, I mean schemes. I was going to say regular schemes, but I don't mean that.
What is
normal schemes.
Is locally a finite presentation just a condition on the underlying schemes, or is it also something like the log structures?
Oh, wait.
Oh, sorry.
I'm only working with fine log schemes here.
Okay.
So that's already some finite this condition, isn't it? Yes. Right. Everything here is a fine log scheme. I don't know if that answers the question, but
it makes it
some
more,
kind of finiteness condition.
It makes it more reassuring that you
Yeah.
might just impose the condition on the schemes and not worry about that.
Okay, so I'm not going to go through all the different things about relating this to differentials and stuff. I'll state some things, but what I do want to do is give some examples of morphisms that we can prove are smooth, which are going to be kind of prototypical smooth morphisms of log schemes. So here's the proposition. I should say, if you want to see the definitions of formally smooth and formally etale and formally unramified and unramified and all the other stuff, it's all in Ogus. Yeah, of course you can separate smooth into formally smooth and locally finite presentation and so on. Okay, proposition. Let's take P and Q to be finely generated integral monoids. And let's have a homomorphism from Q to P, which I don't think it needs a name. So Q to P, a homomorphism. Introducing an ideal domain for this one, something with groupifications. So we're using phi between the groupifications. So then, if the kernel and the torsion in the co-kernel, if these are finite and their order is invertible, in some ring R, then I'm going to map we just take it as there's a spec RP to spec RQ. Then this thing is smooth. So these things are all kind of prototypical log schemes, and this says a condition for a map between them to be smooth.
Aren't they always finite if P and Q are finitely generated? Because then Q group and P group.
Yeah,
Oh, wait, couldn't just
no, they could have bigger rank. Yes.
Our kernel is finite. Yeah, sorry.
Yeah.
I was looking at co-kernel tools.
Yeah, but they could have bigger rank. Yes. And if we want to say etale, then we should look at the whole of the co-kernel, not the torsion. So I think we may have seen some examples of this already. So, map from n to n, sending n to 2n. That gives us example 1. So map from n2 to n2, sending ab to a plus b. That gives us the blow-up example. And the map from n to n2, sending n to n comma n. That gives us the, it's not there anymore, the degenerating scheme example. Okay, so the examples we've seen actually all are of this type, taking R to be the field. So why are we so interested in these things? Well, when you study smooth maps of schemes, you have a theorem that says etale locally, a smooth map of schemes looks like affine space, relative affine space. And there is a corresponding theorem for log smooth maps of log schemes, which is going to be that etale locally, such a thing looks like one of these maps. And so that's the next theorem. So conversely, here's this theorem. So we're going to take a map f from x to y of fine log schemes. And we're going to take a chart for y. So Q to my is going to be a chart. So we assume y has a chart, so this is a chart. Then f is smooth if and only if. So, two conditions. So the first condition is when you just look at the monoids, then what's going on looks like this. So that's etale locally on x, and right, etale locally means in the classic scheme sense. There is a chart d to mx such that the kernel and the co-kernel, torsion part of the co-kernel of the induced map P group to P group finite of order invertible on X. Okay, so this says that the map of monoids looks like one of these things, but we also need to say that our actual map of schemes also looks like this. So condition 2 is, so what do I have? Here's y, and having a chart on y is the same as having a map from y to z of q. And we've also got a map from spec P produced by this map of monoids. And right, condition 1 says that map is smooth. So then, to complete this, we have a fibre product here. So take the product over spectator cube, you get a fibre product. And where does X live? Well, X has a map to Y, and it has a chart locally. So it has a map there, and that means we get a map here by the fibre product property. And this thing should be etale. So this is the equivalent to saying that this map from X to Y locally looks like affine space over Y.
Is it not smooth, maybe?
Right, so...
I think if P and Q are both 0 and the log structures are trivial.
So I think you can, I think it's equivalent.
It's equivalent. Oh, yeah, weird. Okay, I'll think about it later.
Yeah. Yeah, I think it's equivalent. You can ask him either. And I can write the job here, and I can delete that. I get another theorem. Okay, so it kind of says that if you understand what these types of morphisms look like, then you understand etale locally what smooth morphisms look like.
I guess the difference between requiring etale and smooth depends on which chart you pick, right?
Yes,
The assertion that there exists a chart.
Yes.
I'm just confused if the log structures are all trivial, but we have a long break where I can become unconfused. So.
Yeah, I'm pretty sure they're equivalent. Okay, let me just start. The thing with the differentials goes through exactly as for normal old-fashioned schemes, but for example, so relationship with differentials is as for classical schemes. So for example, f of x to y smooth implies that angle 1 x over y is locally free of finite type. As usual, you need to be a little bit careful if you want to try and go the other way, because you probably need to say it should be of the correct rank as well. And if you have a map, so if you have a map between smooth schemes, then saying when it's smooth is something you can easily do with differentials. Saying when a map between schemes that are not themselves smooth over a base is smooth is more confusing, I think. So it's just as usual. Let's note that, so all the examples we've seen just look like this, but I can make a kind of more interesting example that was not one that I could just construct in the old-fashioned way using sheaves of logarithmic differentials. Namely, if I take this family that we had before, which is a smooth curve degenerating into a double point, if I base change to the closed fibre, I'm going to get something more interesting. Base change to special point, special fibre. So that gives me something like a map from this curve with a double point to a point. But this this thing down here is now a log point, because I had a log structure on this and I pulled it back by the base change and I have a log structure on the point. So it's now a log point, not just a point. And this has some kind of interesting log structure. And this thing will still be smooth, because being smooth is preserved under base change. So we get a genuinely new kind of example that we didn't have before when we were just considering log structures coming from divisors. And indeed, I think this is what we're going to be hearing a lot about very soon. Okay, there's one more thing which I was asked to talk about, which was integral morphisms. So let me say the small amount that I know about integral morphisms.
Before you read
yes, sorry, questions first.
And then the last line there. Is there no part coming from the line next to the line?
I think not, because the x and y entirely just depend on the monoids.
Yeah, but still there is a relative sheaf of differentials. Yeah, but it's covered by what's there already. Is it already included in this?
Yeah, I think it's all in there already. Yeah.
Okay.
Okay. We're going to need apparently to know something about integral morphisms. So this comes from the fact that if I have a diagram, if these things are integral lines, then the push out is not necessarily an integral monoid. Okay. We don't like this, or at least we want to characterize when it happens. So we have a proposition. So Kato has a proposition which states he has 5 conditions, and the proposition is that conditions 1 and 4 are equivalent, and conditions 2, 3, and 5 are equivalent. So let me tell you what conditions 1 and 4 are. So we're going to take H from Q to P from a morphism of integral y's. Then the following are equivalent. So firstly, this happens universally. So all Q to Q prime. The push out is integral. And 2, right. Suppose I have H of A1 plus B1 equal to H of A2 plus B2. So this means the A's have to live in Q and the B's have to live in P. Then there exist A3 and A4 in Q and B in P such that B1 is H of A3 plus B, B2 is H of A4 plus B, and A1 plus A3 equals A2 plus A4. Okay, now I think I convinced myself yesterday that if these things, if H is injective, then this one follows from those two. Okay, so this looks like a, I don't know, I don't think it looks like a very natural condition. But, however, David and I managed to work out something that does not satisfy this, which will aid your intuition no end, I'm sure. A morphism like this is called integral. A morphism of monoids. Okay, example. Let's take H from N2 to N2, AB to A plus B. So this is a map we've already seen. This corresponds to the blob. Right. Let's take A1 to be 0, 1.